So let's take a look at carrying out a hypothesis test. So we're going to imagine a study which is trying to tell if people can tell hot and cold water apart just by the sound of the water pouring into the glass. And I should say, if you listen to those sound clips, they're being poured into two absolutely identical glasses. So first we have to ask ourselves, what percentage of people would get it right if there was no difference, if they were just guessing randomly? Certainly isn't the case that everybody would get it wrong. You were guessing, you'd get it right 50-50 chance, right? Equally likely to get it right or wrong. So if you were guessing randomly, the probability you would get it right, the percentage of people who would get it right, would be 50%. So we want to know whether people would get it right 50% of the time or more than 50% of the time. And that's what we're going to use to make our two hypotheses. And notice when I say that, I'm asking a question about people, about everyone. I'm asking about the population parameter. What percent of people would get it right? That's a question about P. Our sample statistic, P hat, we're going to know what it is. That's the percent of people in our study who got it right. But we want to know, based on our sample P hat, what can that tell us about the whole population parameter P? So we have to decide which one is going to be our null hypothesis and which one is going to be our alternate hypothesis. And the thing to remember is that the null hypothesis is always a guess about what P is equal to. And it's usually the boring thing. It would be boring if people couldn't tell it apart. So, and I just realized that for some reason this program lost my subscripts. I had them set up and they didn't carry through. So that's H naught, and that 0 should be a subscript, but it isn't. Oh well. So our null hypothesis is that people just guess randomly and they get it right 50% of the time, that P is equal to 50%. The alternative hypothesis essentially says, no, that's not what P is equal to. It's going to be an inequality, a not equal. We're not saying people get it right 75% of the time. We're just saying they get it right more than 50% of the time. They do better than chance at telling cold water from hot water. Okay, so we've set up our hypotheses. And let's imagine that we've done a study and we've gone out and we've collected some data, and I'm not telling you what the N is or the P hat is, just that we've done a whole hypothesis test and come up with a P-value of 0.34. What does that mean? It would mean that if people were guessing randomly, there would be a 34% chance they would get at least as many right as we saw in our study. So let's say, would you convict somebody on evidence that would have a 34% chance of happening if they were innocent? No. If this evidence would come up 34% of the time if they were completely innocent, that's a third. I'm not prepared to say they're guilty. So a p-value of 0.34, we'll also say 34%, is pretty big. It said this data would happen, a third of the time if the null hypothesis is true. So that is too large to conclude that the null hypothesis is false. It's too large to reject the null hypothesis. So just to repeat myself, a p-value of 0.34 would mean you cannot reject the null hypothesis. You could entirely plausibly see this data if people are just guessing randomly. The population parameter P might well be 50%. You have not proven that P is equal to 50%, just that it is plausible that it could be. So what does a large p-value tell us? If P is large, we cannot reject the null hypothesis. It might well be true. If we put it on trial, we're saying, based on this data, that it's not guilty. That's different from saying that it's innocent. We're simply saying that the evidence is not strong enough to convict it. Might be guilty, might not be true, it might be. Our data doesn't convince us that it is false. So what do we mean by large? Usually, if it's bigger than 5%. 5% is sort of the magic cutoff number that people tend to use. So what if the p-value is small, like 0.3%? That's 0.003 as a decimal. Well, this would tell us that if people are just guessing randomly, if they can't tell the difference, they would only get this many or more right about 0.3% of the time. That's incredibly tiny. In other words, this data is inconsistent with the belief that the null hypothesis is true. You'd be incredibly unlikely to see this data if people were guessing randomly, so our conclusion is they weren't guessing randomly. They really could tell the difference between them. People have a better than 50-50 chance of telling which one is cold and which one is hot. So a small p-value, well, a small enough p-value, allows us to reject the null hypothesis. Small means less than 5%. So if p-value is 0.3% or small, you reject the null hypothesis. You could not plausibly see this data if people were guessing randomly. The population parameter p is not 50%. It really is bigger than 50%. And taking it back to the language of the original problem, we would conclude that people really can hear the difference between hot and cold water. Okay, let's run through a calculation. Now let's look at some data. Let's say you had an N of 145, that's 145 people doing your study, and that 85% of them could tell hot from cold based on the sound. And the studies really have shown 85 to 95% of people can. So we want to carry out the hypothesis test, determine the p-value, and draw a conclusion. And I'd encourage you to pause now and see if you can do that. I'm about to do it on the next couple of slides. So we know the setup of our hypotheses. The null hypothesis, the equals, would be that p is equal to 50%. The alternative hypothesis, the inequality, would be that p is greater than 50%. We've got our data. We have an n of 145 and a p hat of 0.85 or 85%. And it's really important when you're doing these to keep straight your p hat and your p, because you have to be sure you know which one to use in which place. We're going to assume h naught is true, and the people are just guessing, randomly, can't tell the difference. So in this situation, if h naught is true, we know that the percentage of people who would get it right if they were just guessing randomly would be normally distributed. That's because we had at least 10 successes and at least 10 fails, with a mean of 50% and a standard deviation of the square root of pq over n, which is 0.04 or 4%. And with this setup, the question, what is the probability that more than 85% of people will get it right, is a problem that I could have asked you on the last test. So here we have it. Mean is 50%, standard deviation of 4%. What's the probability of a single study getting a p-hat of 85% or above? And here I would like to go to my normal curve and draw a line at 85% and shade in the area above that, except 85% is like way off this curve. The normal curve goes out to like 62. Our z-score, if we take 85 minus 50 and divide that by 4, we get 8.75. So our z-score is absolutely enormous. So pause for a moment and make sure you know what this says, because this says something really convincing. Are we going to get a small or a large p-value? What conclusion are we going to draw? So what's our p-value? Well, our z is 8.75, and that's like off the charts. So what is the area above to the right of that z-score? The area to the left is basically 1. The area above to the right of it, 0. So the p-value is tiny, 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 tiny. Close enough to 0 makes no difference. So is the p-value that small? We reject the null hypothesis. Small p, reject. So we reject the null hypothesis. We conclude that people are not guessing randomly and that they do a much better than chance job at telling which is hot and which is cold water by sound. And this last sentence here, this is where I go from kind of probability speak, reject the null hypothesis, to telling you about the actual situation I care about. Can people tell hot and cold water apart by sound? Yes. And every time you do a hypothesis test, you should do this. You should finish by just telling what it tells you about the original situation. One last thing to say here. I had you guys go out and collect data, and our study actually had a problem. I got 35 answers, and 31 people got the water sounds right. That means a p-hat of 31 over 35, or about 88.6% of you did. So what's wrong? Why couldn't I use this data to carry out a hypothesis test? Not enough people got it wrong. The study was too small. Only 4 people got it wrong. So we had 31 successes, but we only had 4 failures. So that was too small to use a normal curve. We couldn't use a z-table. Oh well. Okay, great. I'd like you to go do the remaining Quizlet, which is a homework type problem, and see how much sense hypotheses tests make now.